Hello, everybody. My name's Bret Weber. I'm Executive Vice President of Global Engineering Operations at DDN and also CTO. And so I wanted to talk a little bit about the adoption trends for solid-state technologies in our big data sites. So just a couple of quick slides first about DDN. We're not a huge company, so a lot of people don't really know who we are, but we were founded in 1998, so we've been around for quite a while. We're actually right now, I believe, the world's largest private storage company because I think everybody else has been bought. So we're it now. We're definitely profitable, double-digit growth, self-funded, and then our headquarters is in both Santa Clara and Chatsworth. And we do have a global presence. I've got engineering facilities in Silicon Valley here, in the LA area, Colorado Springs, in the federal area in Baltimore, Maryland, as well as development facilities in Paris as well as Pune. So one of the things that we've done is we've really concentrated on essentially the big data space and really the commercial big data space. So we are very much looking at applications and very concentrating on application acceleration. So as well as just the traditional technical supercomputing, we're also in financial services, media space, manufacturing, and then life sciences and genomics, of course, and then also a lot in the web, cloud, and telco space where a lot of people don't normally associate us with. So the game has changed quite a bit, and so over time, we're not really seeing, and this kind of goes back to what some of the previous speakers were talking about. It's not just about, I want bigger, better, faster anymore. Where originally it was, I just want my primary storage and I want more IOPS and I want more bandwidth and I want a parallel file system in front of it. So more and more, we're actually seeing people that want to be flexible in terms of what they have. So, burst buffer, that's, certainly the talk now, but also things like active archive, object store, even tape. Tape's not going to go away anytime soon, but really they want the flexibility and the management to go end to end with the data. And so that's what we're really seeing. And so what we've tried to do is we've tried to build a flexible infrastructure so that we can adapt to the different RFIs and RFPs that come through. So next, I'm going to talk a little bit about some of the trends that we're seeing, especially with respect to flash. So this is a little bit kind of talks about really the end-to-end capability. And so over here on the right-hand side, you've got the cloud. People are really starting to talk about web at-scale cloud and really want to be able to migrate data into the cloud. But also object stores are very, very popular right now. And so guess that doesn't work. The WAS, that's our product. This is organically developed at DDN. This is an object store. It doesn't have a traditional underlying file system because the underlying file system would tend to fragment the key value. So essentially, we've developed that. We've put that at customer sites where we actually have customers that have over 100 billion objects in our WAS platform. And so in addition, we've got the normal, very fast, redundant storage. This is our SFA 14K. And traditionally, the parallel file system is sitting in front of this. This is the block store that is underlying. But what we found over time is really that we can make that block storage just as fast as we can possibly make it. But if you look at the application level, in many cases, speeding up the block storage doesn't mean speeding up the application. So what we did is we launched another organic development within DDN called IME, or Infinite Memory Engine. That's the one over at the left-hand side. And this is the other one that a lot of people might call it a burst buffer, and in some cases it is used as a burst buffer, but we looked at it more from an application accelerator. We wanted something that would take these malformed IOs and really, independent of how the application was written, still add value to the application and increase how quickly it would execute. So in terms of SSDs and non-volatile memory, where we're seeing people really asking for it is, of course, in the burst buffer layer with NVMe. We have products out in the market that are dual port NVMe for the highest speed. We see that in this IME layer. Also a little bit in the SFA block storage layer. In addition, accelerated metadata, we see that in both areas, and accelerated application data sets where people want to prefetch data sets into this SSD, and they might want it in the block storage, they might want it in the burst buffer layer. And then we also see some cases where they want to do some acceleration into the cloud layers also. So what we did was we went back and we really looked at all of our RFI, RFP trends in terms of flash and what are people really asking for now. And so this is in many cases based on RFI participation, and then we just kind of went back through and we combed it. And so over the last several years, the percent of primary storage bids with SSD has increased from roughly 25% to 75%. So we're seeing a lot more of these primary storage bids wanting to really be more hybrid. And so SSDs now, as a percent of drives in deals, we've seen that increase over 500% in the last several years also. So a lot of this is the trend of the speed going up, the price coming down with the SSDs. And then one of the things that we also see is in commercial accounts, we're 3x more likely to include SSD in a purchase than traditional HPC accounts. We're still seeing it in both, but we're seeing it 3 times more in the commercial big data space. And so also the ratio of SSD to HDD purchasing is roughly about 3x higher than what we have seen in traditional HPC over time. And so, as I mentioned on the previous slide, the biggest technology inquiry growth areas have been, it's really SSD, object storage, active archive, and cloud, both private and hybrid. And so this is really, I think, reflecting the case where, I don't want to just buy a parallel file system. I want really the end-to-end management across all this, and I want the flexibility to put the SSD where it can do my workflows the most good. So over time, we've seen an evolution of mixed I/O performance coming out. Traditionally, on the left-hand side, you just basically had drives there and rated it. With our SFA, we have the what we call a React technology. This is essentially where you can do full stripe writes to rotating media so that you don't have to actually do the cache mirroring, get back the command complete. It's been around for quite a while, but then what we did was we added to that the SSD capability with our SFX technology. The SFX technology allows us to use SSDs and provide some read cache capability with it. And then lastly is the IME, which now that's sitting above the file system, and so this is where we can get around a lot of the bottlenecks that the file system is causing, and so we can really start to accelerate the applications. So I'm going to go in very quickly to each one of these. This is the React capability where essentially full stripe writes come in, we can go directly to the media. This gets you a very low dollar per gigabyte per second because the rotating media prices are very low, and capacity-wise can get you quite a bit of capacity. But meanwhile, you have mixed I/O, and so you have a lot of small block I/O, which typically you want to mirror across the caches, but you don't want to, you don't want to fill up the cache with full stripe writes. So that gives us the capability to essentially separate them dynamically. Also with the SFX, if you look at the left-hand side, is really traditional read cache capability, to where things come into the read cache. We have 4 LRU buckets for that. And then we also have the instant commit capability, which essentially is pre-warming of the cache. And so anytime a write comes in, we can pre-warm the cache for the read back. But where we kind of changed a little bit is we added the context commit capability. And so this gives us both an in-band hinting capability with essentially Intel Luster, where they've instrumented the file system. It goes across on a per IO basis on the SCSI IO, and then we can take that hint and then we can populate our SFX cache accordingly. But in addition to that, we also have an out-of-band capability. So the out-of-band capability actually translates up into the file system, where people can specify either working directories or files that they want put into the SSD read cache ahead of time. We'll go prefetch that in. This can be integrated in with the scheduler. In addition, with the M-band hinting, we've also added capability where at the Luster we can use fadvise, and so at either the application level we can use fadvise to send down hints to the applications, or in addition, we can do that from a command line standpoint also. So this adds some more capability depending on how much trouble you want to go to with your applications. So it's everywhere from set it and forget it to I want to write my application specifically for it. And so this is a case with Purdue University where we worked with them. They just use some of the basic SFX capabilities, and they've been very happy with it in terms of accelerating their workflows. They've seen quite a bit of improvement with that. We're working with them to take it really to the next level and what they can do with it with some of the in-band and out-of-band hinting. So now let's move over to IME. IME stands for Infinite Memory Engine. It's a marketing term. So it's essentially a software application accelerator. We don't look at it as just a burst buffer, but we leverage the non-volatile memory and the SSD to really remove system level performance bottlenecks. So we can get high bandwidth from it, we get low latency. We also, one of the things that we bring to the table with that is really the data integrity and the redundancy level, because now, this is, I think, where we differ a lot from a lot of the normal traditional burst buffers is we actually provide redundancy across that SSD. It also provides massive scalability. You can continue to add units. And then we've done this from a standpoint of hardware, being hardware agnostic. We don't want to tie ourselves to the hardware, but yet we will offer appliances where we can provide the best performance. So with our IME implementation, we really had in mind going anywhere from node local to an appliance level where everything is centralized in there. And so we definitely wanted to keep POSIX compatibility for all the commercial big data applications, because these guys, they're not going to change their applications, but they still want them accelerated. And that's some of those cases I talked about before. It's the oil and gas, it's the life sciences and genomics, it's financial services, and also manufacturing with ANSYS workflows, other things like that. So, that gives us the capability to where we can absorb all the I/O into the SSD, and then what we do is we go back and we pull that out and we reorder that I/O so that we can then stream it into the parallel file system. And so in many cases, you can either downsize the parallel file system and absorb any of these bursts, or there's certainly a lot of other cases where it tends to help you in application acceleration. And so this realignment of the I/Os can allow you to have an application that's not written well, and especially not from a standpoint of a parallel file system, but still get application acceleration from it. We also have capability that we've designed into this for API integration in with the job schedulers, so that we can actually do prefetching of data sets in here. So this is just a high-level block diagram of how it fits in, how it fits into to the overall picture. You've got your compute cluster, and essentially you've got both IME and parallel file system clients that sit in here. And so in this burst buffer application, you can see IME actually really sits in the path. Now, we still have the parallel file system mount point, but you can also choose the IME mount point. And so the IME mount point is where you're going to have all the SSDs, and so you can do those writes. Then we'll replay it to the parallel file system, and then the IME at that point will become a parallel file system client, and then rewrite it into the parallel file system. And then at that point, we also have the capabilities to migrate out of the parallel file system into either object store or into the cloud at that point. So this is a quite a bit older use case scenario that we use. This was with iCheck, and this was an oil and gas flow. I have some better ones in this, but I couldn't get the customer release in time to incorporate them in. But this really shows cases of what it looks like baseline into the Lustre file system traditionally, also the in-memory, and then in the case with having the IME in between to give you a feel of what kind of accelerations you can actually get with it. So you do start to approach the case of in-memory. So this is really kind of the big picture to start from, and as we see the RFIs and the RFPs coming out, not everybody knows where they want the SSD or what they actually need, and so this gives us the flexibility that we can actually populate it where the application workflow can accelerate it the most. And so in this case, you can see the compute clusters. In this case, we've got Scratch on Exascaler, and then these 6 units over here are the scalable IME units. These have SSD in them. And then down below, we have essentially the home and projects on our grid scaler system. This is GPFS based. And then we have migration across with our grid scaler to WAS bridge, where we migrate out from the parallel file system into the archive on cloud, and then also some NAS capability. So lastly, the IME, the motivation for the IME was really to get around the bottlenecks that just making the block storage faster wasn't getting us anywhere. And so by doing that, we can decrease the storage latencies. We can take these fragmented I/O patterns and misaligned I/Os, and we can essentially aggregate them together. We can pull them out separately and replay them at full speed into the parallel file system. And then also in out-of-core applications, then this tends to accelerate those also instead of slowing down. So, thank you.